Type one command and watch. It takes your question, reaches out to the live web, and reads 5 real sources. Then, a model folds those 5 pages into one clean report, a short summary, the key findings as bullets, and the sources it used. This is a web research agent. One small Python file. No copy and paste, no 10 open tabs. You ask, it goes and finds out. Let us build it, piece by piece. So what is this, really? Not a script that runs top to bottom. It is a graph. Picture 1, rail. Your query enters on the left, flows into the first node, search, then into the second node, synthesize, and a finished report comes out the right. 2 nodes, one edge between them, and a marked entry point. Why a graph and not 2 plain function calls? Because every node shares one thing, the state, and this shape is built to grow. Today, a straight line. Tomorrow, you add nodes and branches. LangGraph compiles that wiring into a single call. Every node shares one object, the state. Think of it as the carrier riding the rail. It is a single dictionary with named slots. 3 you set. When you start the run, your query, max results, how many pages to fetch, and the model name. 3 more get filled in as it runs, search results, the report, and messages, a running record of what the model said. Nobody passes arguments from node to node. They all read from and write to this one shared object. Fill a slot here, read it there. Here is the part people miss. A node does not rebuild the whole state. It returns only the slots it changed. Nothing else. The search node returns just search results. LangGraph takes that little piece and merges it back in for you. And by default, a new value overwrites the old last write wins. One small exception. The messages slot is marked to add on instead of overwrite, so replies stack into a record. It barely matters here with one write. But that is how a real conversation would accumulate, turn after turn. The first node reaches outside your program. It hands your query to Tavily, a search engine built for agents. Tavily crawls the live web and hands back up to 5 results. 5 sources, not one. Each result carries a URL, a title, and a chunk of the page's text, the raw material for the report. But the network can fail, a wrong key, a rate limit, no connection. So the node guards for it. If the call fails, it catches the error and returns an empty list instead of crashing. A good agent plans for the empty case. Now the second node, 5 raw web results are not a report. So Synthesize does 2 things. First, it checks, did we get any results? If the list is empty, it skips the model and writes one honest line, no results, and why. Otherwise, it builds a prompt in 2 parts. A system message fixes the rules and the shape. Return a summary, key findings as bullets, and sources. A human message carries the query and all 5 results. Temperature is set to 0. Higher numbers add randomness. 0 keeps it factual and steady. The model reads it all and writes the report. Step back and look at the whole flow. The graph itself is a straight line. The entry point is search. Search always runs first. Then, the single edge leads to synthesize. Then to end. There is no fork between the nodes. The only decision lives inside synthesize. Did we get results or not? Yes, and it writes the real report. No, and it writes the fallback line. So remember the split. The edges set the order between nodes. The branching logic lives inside a node. Small today, but it is a real graph. That is the theory done. Now we write the code. Grab your laptop and build along with me. I will walk you through what we are doing and why at every line. On to agent.py now. We'll take it step by step. So to kick things off, the very first code that runs when someone starts this program is our main function. An import pulls in code that already exists so we can reuse it, and argparse is Python's built-in library for reading command line flags. The def keyword defines a function, a named block of steps we run later, and we name ours main. Inside it, we create an argument parser, the object that reads whatever options the user types after the file name. Now we describe the flags a user can pass. This first one is the query flag, the research topic the agent will look up. That default value is our safety net. If the user runs the program with no flag at all, we fall back to a built-in query so it still does something useful. The help text is the one-line description shown when someone asks the tool how to use it. The next two flags lean on some settings, so let me lift those up top as named constants. A constant is just a value we set once and reuse by name. Default underscore model holds which OpenAI chat model to call, and GPT-4o mini is a small, cheap, fast one. Default underscore MA underscore results is how many web results to fetch, 5 by default, and naming it here means one edit. Changes it everywhere. Here are the other two flags. The max results, one has type equals int, which forces the text the user types into a real whole number we can count with. Both borrow the constants we just defined as their defaults. That little f before the help string marks an f string, a string where anything inside curly braces is swapped for its live value, so the help message literally prints the current default. With the flags described, we call parseArgs. It reads what the user actually typed and hands back one object we name args, holding every value. Run with nothing extra, args.query now equals that default. Latest advances in AI agents 2024. That is the single real example we will follow all the way to the printed report. Before we spend anything on paid APIs, we call check-n. If a key is missing, we want to stop right here with a clear message rather than crash deep inside a network call later. We have not written check-nv yet, so let me build that whole function right now. Check-nv reads secret keys, and those live in a file, not in our code. This import brings in load_.env from the Python.env library. Its whole job is to read a plain text file of key and value settings and load them so the rest of the program can see them. And here, we actually run it once as the file loads. After this line, anything we saved in our .env file is available through the environment, exactly as if we had typed it into the shell ourselves. Without this call, those keys would simply not be there, and check-nv would turn us away. Two more built-in libraries. OS lets us talk to the operating system, and we use it to read those environment variables. Sys gives us access to the running program itself, including how text gets printed to the screen, which matters for the emoji we print later. Here is a subtle one worth knowing. Our report prints emoji like the magnifying glass, and on an older Windows terminal, that would clash with an encoding error. This block checks whether the output stream can be reconfigured, and if so, switches it to UTF-8, the encoding that understands those characters. The try and accept mean that if the switch is not supported, we quietly pass and carry on instead of failing. One more constant, and this one is a tuple, an ordered fixed list written with round brackets that cannot be changed after we make it. It names the two keys. This agent cannot run without, one for OpenAI and one for Tavily, our web search service. Keeping the required names in a single place means check-nv can just loop over them. Now the function itself. the arrow. None after the parentheses is a type annotation, a promise that this function returns nothing, it just checks and maybe stops. That triple quoted line is a docstring, a short note describing what the function does. The real work is a list comprehension, a compact way to build a list that walks each required name and keeps only the ones where os.getInv comes back empty, giving us the missing keys. If that missing list has anything in it, we raise system exit, which stops the program immediately and prints our message. The F string drops the exact names that are missing into the text with join, so the user sees precisely what to fix. This is the fail fast idea. One clear sentence up front beats a confusing crash 3 steps later. Back in main now, with the keys confirmed, we announce what we are researching. This print uses an F string again, so args.query drops straight into the line. For our example, it shows researching latest advances in AI agents 2024. Those \n pieces are new lines, blank lines above and below, so the heading stands out. Now, the heart of it. We call buildGraph to get our compiled agent, a function we will define next. Then we run it with invoke, handing over a dictionary, a set of key and value pairs. That is the starting state. Query holds a topic. The other fields start empty, and max results and model carry the flags through. This dictionary is the shared workspace every step will read from and add to. When the agent finishes, result is the final state dictionary and we print the report. That *60 is Python multiplying a string, so equals sign times 60 draws a line of 60 equal signs as a divider. Then we pull out result bracket report, the finished write-up, and print it. That is the whole payoff of the run. Main just called buildGraph, so let me build that whole function now. First, its tools. This import brings in stateGraph, the class we use to describe our workflow as a set of steps, and end, a special marker that means the workflow is finished. Both come from LangGraph, the library that runs these step-by-step agents. buildGraph also promises what type it returns, and that needs a couple of typing helpers. This line pulls in type underscore checking, annotated, and type ticked from Python's typing module. Typed ticked lets us describe the shape of a dictionary. Annotated attaches extra info to a type, and type underscore checking is a flag we will use in a second. Here is that flag in action. type underscore checking is false when the program actually runs, but true when a separate type checker inspects the code. So this import of compiled state graph only happens during type checking, never at runtime. That keeps a heavy import out of the real run while still letting tools understand our return type. Now the function. Its return type is written as compiled state graph in quotes, a forward reference, just a name. The checker resolves later. We create a state graph and hand it research state, the shape of our shared data, which we will define shortly. Then add node registers 2 steps by name, search and synthesize, each tied to a function, search web, and synthesize report that we build next. These lines wire the steps into an order. Set entry point says start at search. The first add edge draws an arrow from search to synthesize, so once the web results are in, we hand them to the writer. The second edge points synthesize to END, marking the finish. Finally, compile turns this description into a runnable agent, the very thing main invoked. Build graph pointed at research state, so let me define that shape now. It needs one more helper. This import brings in add underscore messages from LangGraph. It is a special rule for combining message lists, so that when a step returns new messages, they get appended to the running history rather than wiping it out. Here is the shared state, written as a class that inherits from typedict, which just means it is a dictionary with a fixed, named set of fields. Messages is a list annotated with that add underscore messages rule, so new messages append instead of replacing. Then query is text, search results is a list of dictionaries, report is text, and max results and model carry our settings. Every step reads and updates this one structure. The first real step is search web, and it needs our search tool. This import brings in Tavily Search, a ready-made connector to Tavily, a search service built for AI agents. It takes a query and returns web results already cleaned up for us, so we do not have to scrape pages ourselves. Now the step function. It takes state, our shared dictionary, and returns an updated one, which is how every LangGraph step works. State.get reads max results from the state, and the second argument is a fallback. So if it is somehow missing, we use our default of 5. Then we build a Tavily search tool set to fetch that many results. Here we actually run the search. Tool.invoke sends our query, latest advances in AI agents 2024, off to Tavily and waits for results. Network calls can fail, so we wrap it in try and accept, which catches any error instead of crashing. If it does fail, we print a warning to standard error, the separate channel for messages, and return an empty results list so the program can still finish gracefully. Tavily can hand back its data in more than one shape, so we normalize it. IceInstance checks a values type. If raw results is a dictionary, the list we want sits under the results key. If it is already a list, we use it directly. And the else branch guards anything unexpected by falling back to an empty list. So the next step always gets a plain list. To close the step, we report progress. Len gives the number of items in a list, so this prints how many sources we found. 5 for our example. Then we return a small dictionary with just search results in it. LangGraph takes that and merges it into the shared state, so the next step can read the sources we just gathered. The last step turns those sources into a report, and it needs 2 more tools. The first import brings in human message and system message. The two kinds of message we send a chat model. A system message sets the model's role, and a human message is the actual request. The second import brings in Chat OpenAI, our connection to OpenAI's chat models. Now the writer step. It reads search results out of the state. Then, if not results, guards the empty case. Because if the search came back with nothing, there is no point calling a paid model. Instead, we build a helpful message explaining what likely went wrong and return it as the report. This is defensive coding, handling the bad path before the happy one. If we do have results, we set up the model. We create a chat OpenAI client, passing the model name from the state, GPT follow mini by default. Temperature equals 0 is the key setting here. Temperature controls randomness, and 0 makes the model as focused and repeatable as possible, exactly what you want for a factual report rather than creative writing. Before we can ask the model, we flatten the raw results into one block of text. For each source, we pull out its URL, title, and content, and if any piece is missing the or gives us n/a instead. That slice on content keeps only the first 500 characters, trimming each source so the prompt stays small and cheap. Join then, use them together with blank lines between. Now, we build the two messages we send. The system message sets the model's role. It tells the model to act as a research analyst and to structure the report with a summary, key findings as bullet points, and sources. The human message is the actual request, and it stitches in our query and all that results text we just prepared. This is the instruction plus the data side by side. This one line does the real work of the whole step. lm.invoke sends both messages to OpenAI and waits for the model to write back. The reply comes back as a response object, holding the generated report along with some metadata. This is the single paid network call in a normal run, so everything before it was about preparing this moment. We reach into the response for its content, the actual text. Usually that is a plain string, but some newer models return a list of content blocks instead, so we check its type. If it is a list, we walk each part, pull out its text, and join everything into one clean string. This little guard means the rest of our code can always trust content to be printable text. And the step returns its result. This dictionary carries the finished report text back into the shared state, and it also adds the model's response to messages. Remember that add_messages rule on the state? This is where it earns its keep, appending the reply to the history instead of overwriting it. After this, the graph reaches END and main prints the report. One last piece ties it all together. This is the run guard, and dunder name is a built-in variable. Python sets to the string dunder main only when you run this file directly. So when we type the command, this check is true, and it calls main, starting everything. If another file imported this one instead, the block would be skipped. That is why nothing runs on import. Now we move on to requirements.txt. Let's walk through it together. Before any of that code can run, we need its libraries installed, and this file lists them. A requirements file names one package per line, and the double equals pins an exact version so everyone gets the same behavior. We see LangGraph that runs our step graph, LangChain Tavily for web search, LangChain, OpenAI for the model, and Python.env that loaded our keys. You install them all in one go with pip. Now we move on to .env. Dot. Let's walk through it together. This is the file our program actually reads for secrets, and you create it yourself. Each line is a name, an equal sign, and a value, with no quotes and no spaces around the equals. OpenAI underscore API underscore KEV is the key that lets us, so that is the whole agent, a shared state that rides the rail, a search node that calls the live web through Tavily and returns 5 sources, a synthesize node where the model turns those 5 results into a summary, key findings, and sources. 2 nodes wired as a graph compiled into one call. Change the query and it researches anything you want. And because it is a graph, the next step is simple. You just add another node.